My name is Tomasz Wasak. I come from Toruń, and in this talk I would like to present to you some of the results about cavity-induced effective atom-atom interaction that originates from the coupling of single atoms, of single photons to pairs of atoms. And this work was done in collaboration with Sankar Sharma from the University of Toruń and with Jan Chwedeńczuk from University of Warsaw. So here's the brief outline of the talk, of the presentation. So first I will describe the light-matter interaction, in particular this photon pair interaction, and then I will tell you about a simple application where we can use it with double well potentials, and then how to generate the entanglement with the interaction, and how you can extract this interaction entanglement. And I will finish with outlook and conclusions. So what is interesting in all the interesting states, or most of the interesting states in many body systems, result from the form of the interactions between the atoms. So one promising way for tuning the interactions is through photon exchange in optical cavities. So where atoms are placed inside the cavity, they can exchange photons with the cavity or with the pump, leading to effective long-range interactions because the photons encompass the volume of the cavity. So this is the long-range nature of the interactions. So as we heard today, about a prominent example is the self-ordering with a cavity in a Bose-Einstein Bose-Einstein condensate in a cavity, which was done as was told today by Tilman Esslinger. And here's the review where such experiments are theoretically reviewed. So these types of interaction engineering enables quantum simulations of solid states, Hamiltonians, and can go also beyond. But such schemes with atom interactions involve a single photon interacting with a single atom. So this type of interactions after result from adiabatic elimination of the photonic degree of freedom and of the excited state. So what we are left with the Hamiltonian for the ground state atoms with the non-local type of density interaction, but this has a long range nature. And this leads to this type of self-ordering, and one can also try to harvest the possibilities provided by the multimode cavities and even engineer this type of interaction with more modes in the cavity, which led to the experimental observation of phonons in self-ordering, and theoretically to new states like supersolids with or some droplet phases in such a ring cavity geometry with condensate. So this was this paper of Helmut Rich and Farok Miverfar. So, but recently there was a paper in which the formation of pair polaritons was experimentally demonstrated with fermions, ultra-cold fermions, and where they observed a strong coupling between a cavity and a pair of fermions. So the experiment directly showed that it's possible to couple pairs of fermions from gas to a molecular state by using a single photon. And what they observed in the spectrum is the typical spectrum of polaritons, anti-crossing of that is typical in polaritonic experiments. So if we have this type of coupling, how to describe this? So we have an atomic pair annihilated, we annihilate the photon, and we generate a molecule. So that would be a simple Hamiltonian that describes this kind of processes. And it was in fact used in the literature, but more in the context of producing molecules. So when you do the adiabatic elimination of the molecular state, what you're left is the atom-atom interaction, which is local, and you have this position dependence given by the mode of the cavity, and we also included the cavity transversal drive from the perpendicular direction, but you can also pump the cavity mode directly. So omega r squared over delta A, well, delta A is the tuning from the molecular state, is the photon-induced interaction strength. So what is important here is that we get a photon-induced atom-atom interaction, which preserves the photonic dynamical degrees of freedom, because we have this photonic mode here, which carries the operatorial nature of in quantum mechanics, which is in contrast to standard schemes when we couple single photons to single atoms, because then after adiabatic elimination, the photons are slaved to atomic motion, and there's no photonic degree of freedom there. So once we have this kind of interaction, we can use it for something, and we applied it to a Bose-Einstein condensate in a double well potential like this. And for a simplified description, we have assumed the localized states are centered around the minima of a double well potential, and the transversal drive, which might be useful for something else, is turned off. And we approximate the field operator of the ground state with these two bosonic annihilation operators of the localized modes. And after introducing some Schwinger representation of angular momenta with these two bosonic operators, we arrive at the total Hamiltonian, which consists of three terms. One is in the reference frame of the laser, pumped laser, we have the photons, the pump, and we have the interaction, which is the jz squared in this language, and the tunneling between the sides. And the atom, so this is bosonic Josephson junction. And light matter interaction is described by this part when we have these operators here, because they are proportional to the number of number operator, because there is no transversal drive, and we have this gz squared, which comes from the interactions. So jz squared term is similar to one-axis twisting protocol that we already heard at this conference. And we assume here that we are starting from an equal superposition of the atoms, so all atoms occupy as a single mode. And by raising an interval barrier, we can get rid of the tunneling, and let the particles correlate by atom-atom and this photon cavity-induced atom-atom interactions. So in standard one-axis twisting, Jz squared reduces atomic fluctuations and lead to spin squeezing, which can improve the sensitivity over the shot noise. So just to remind, we have heard Stefano's talk today about quantum Fisher information, so this will be extremely brief. So what I like about Fisher information, this perspective, is that it's the highest susceptibility of the state in response to some perturbation composed of n particles. And the theorem is that if you have separable states, quantum Fisher information is bounded by something that is linear in A, which is the shot noise limit, or standard quantum limit, as they call it. And we have the Kramer-Rao bound, which sets the precision of estimation theory, in estimation theory. For me, what is important is that the quantum Fisher information can serve as an entanglement criterion if we break the shot noise limit, and the maximum is the Heisenberg scaling, which is proportional to n squared. So we're doing the numerical calculations, and we're interested in atomic subspace. So we're tracing out photonic degrees of freedom. And calculating quantum Fisher information for the mixed state is in general challenging, but what we arrived at in some approximation is that the quantum Fisher information is of this form when we have a crossover from shot noise to Heisenberg scaling given by this dynamical crossover function. And what is interesting here is that the effective coupling, which appears in the time scale, this tau q, carries this square root of n total number of atoms. So it's a consequence of the coupling of photons of atoms, collective coupling to photons. And the power is quite funny. So here's the Hughes-Q function, and without the cavity and with cavity, and they are very different for the same time. And what we have is that without loss, we're pumping from the empty cavity, and without loss and with loss, the numerical calculations, this black and analytical, this green, are quite in agreement. And this here we compare it with the case without the cavity. And what is interesting is that even with quite large losses, we get the Heisenberg scaling, which half of the Heisenberg scaling, but the time scale is slowed down. So we ask ourselves about the universal question about optimal measurements, because physical measurement always yields the classical Fisher information. And so the classical Fisher information is bounded by quantum Fisher information. So this is what we have access to. So we are doing this scheme that we rotate first before we rotate the system atoms with some variable angle before applying the measurement, and we are measuring the population difference between the wells. So this translates in this language of operators to eigenvalues of JZ. And what you find is that we do the scan over all angles, and we find that we can find an optimal angle that is optimal for all the times. Even though the state is in a mixed state, the atoms are lossy, we find an optimal measurement, the single theta, even for large losses, and for most theta, classical Fisher information exceeds the short noise limit certifying entanglement. And I think I have to be converging to final slide. So in the pulsed scheme, we also apply the pulse scheme, and we have seen that even with large losses, we get high Fisher information. So the surviving quantum Fisher information demonstrates highly entangled states even in these transient regimes when we get rid of photons. We also investigated Bell correlations, but I will not, which appear quite quickly, but I will skip that. And so with this new cavity-induced atom-atom interaction, there can be novel schemes for entanglement generation of atomic samples by coupling to photons. But what is also interesting in the context of self-organization is the self-organization induced by this new type of interaction. So we're investigating this direction now in a Fermi gas in collaboration with Sankar Sharma, Farok, Miver, and Helmut Rich, a group from Innsbruck. And some preliminary results show that they are very preliminary, and I will not describe them. So, but we see some signatures of self-organization in this setup. And recently there was an experiment in that in a group of Jean-Philippe Brantou in collaboration with Eugene Demler, and they really, using this kind of this kind of interactions, they show coupled changer pair density waves. So arriving at conclusions, so I told you about how to go beyond single photon coupled to single atom, and this is by coupling pairs of atoms to single photons. So the effective interaction depends on the photonic degrees of freedom, because we didn't eliminate that adiabatically. And with that, I told you about the scheme in which we generated entanglement and belt correlations, but I didn't tell you that. And we found an optimal measurements for extracting the quantum Fisher information. And that's it. Thank you. Thank you.
Are there questions? Yes, we have one down there.
Would you describe how you leave the photonic degree of freedom without eliminating adiabatically?
Sorry, can you repeat again?
Sorry, how do we keep the degree of freedom of photonic degree by not
in the interaction? Yes, yes, because we are eliminating the molecular states. So we are adiabatically eliminating the molecular state, because molecular states are usually quite lossy. So we are far detuned, red detuned, blue detuned from the molecular state. And in that approximation, we're not occupying the molecules. And we can get rid of it from the formalism. And the cost is that we are arriving, or the advantage is that we have an effective interaction between atoms. But the cavity photons are still there, so we're eliminating only the molecules.
I see. So it's almost near resonant. Cavity and the atoms are
yes,
almost
it's present. It's present.
almost resonant.
Yes, yes,
I
yes.
see.
And it has its own dynamics. It can be classical or non-classical. We have found different regimes, but we can also pulse it, but it's a separate degree of freedom, and we have to keep it. In principle, we can eliminate that adiabatically also, but we would get effective many-body interactions in the Hamiltonian.
Thank you.
Thank you.
Okay, thank you. Thank you again.
Thank you.